Hi, everybody. I wanted to I want to greet you all. I'm really grateful that so many people at UWC were interested in learning a bit about programming. Um, this is intended to help you learn how to use programming as part of your research, though. So this is really catering to the interests and needs of biologists, not just people who want to learn programming as an independent thing. Maybe your backup goal is to drop out of grad school and write video games for a living. All of us have ideas about other things we can do, so you can feel free to use your skills for good or for evil. That is completely acceptable. So I would start with saying that one of the most frequent questions that we get from people who are just getting started in bioinformatics is, what language should I learn? And you see quite a few different candidates thrown around. This is just the slide at the moment is just showing a few of the languages that people routinely talk about. I thought it would be worthwhile to talk about strengths and weaknesses of each. But ultimately, I want to tell you that if you learn one of these languages, learning the other languages as well is usually not that big a step. So just because I'm teaching in Python today doesn't mean what you're learning is not relevant if you decide to switch to Java or to C# or to any other language. So I have programming experience in all but two of the languages on this screen. I started out actually in BASIC on my Commodore VIC-20 many years ago. Took in some Pascal, some Object Pascal. When I was in grad school, I did almost everything in Java. When I was a professor, I swiftly changed over to doing a mix of C# and C++ languages. So and nowadays I do almost everything in R. So I've touched a lot of things on this screen, but not all of them. So let's talk about why somebody might choose to use a different language for different applications. We start with the Java programming language. Now Java is kind of long in the tooth at this point. It's been around a long time. It's been through lots of different revisions. There are some amazing libraries out there for it, but it no longer has the panache of the brand new language on the block that it had when I was in grad school 20 years ago, right? So Java is still a brilliant language to learn. If you are focused on learning object-oriented programming, Java is, in my belief, the best language to learn as a first language. But the real claim to fame that Java has held for a long time is the ability to run on many different platforms. In most cases, if you're running an Android cell phone, you have the ability to run Java apps on your phone, let alone on a computer. So being able to run on Linux, being able to run on Mac, being able to run on Windows, this is something that Java does really well, actually. C# is, in many ways, Microsoft's response to Java. It represents a way to create, to use a set of libraries called .NET that allow you to carry out the same functions across many languages, but C# gives you the ability to do it in an object-oriented way that is a nice amalgam, frankly, of Java and C++. A lot of people speak of the language C and C++ as though it's your only option if you want to run code very quickly. That's kind of a misnomer. But the reality is that if you're writing something like a device driver to actually make hardware operate with a given operating system, you're likely to be doing it in something like C or C++. And it certainly has a place within the world of bioinformatics. One of the biggest libraries my team has ever collaborated in, the ProteoWizard library, is principally C++. However, C++ does not have a unique claim to fame on producing fast code. Fortran does as well. Fortran's an ancient language by a lot of today's standards, but a lot of really great numerical optimization has taken place in Fortran that allows you to create numeric code for dealing with really big matrices or whatever in a way that's a lot faster than what you could do in a lot of other languages. Quite often I work in R. I think some of you may have taken a 5-part course with me earlier in February where we talked about the basics of programming in R. R has become very much the language of biostatistics, and a lot of people who are interested in data science also do a lot of work in R. So that's very powerful. Perl is not a language I love. I often say very mean things about Perl. For example, it is possible to write very sloppy code in Perl. It is also possible to write pristine and beautiful and legible and well-structured code in Perl. But the language doesn't require you to be nice and neat and orderly, and frequently that means that people can knock out a bit of code very quickly in Perl to accomplish a task, but it's not, in fact, that easy to read for other people. And finally, I've been probably most trenchant about Python on this slide. I believe big data is a thing. We've all heard, I think, at this point that the fourth industrial revolution is upon us, and only people who can navigate huge volumes of data are going to be needed in the workforce 50 years hence. Well, maybe that's true, and maybe it's not. But it is true that that big data and data science have become umbrellas, organizing principles in the space of bioinformatics and biostatistics. And so Python is one of the languages that is most heavily featured in this new push. I want to stress, though, that if you're doing bioinformatics, any of these languages is a perfectly acceptable way to start. Doing it in BASIC, for that matter, is okay. There are plenty of libraries out there to help you in any of these languages. And which of the languages you learn first is much less an issue than what you want to accomplish, how you want to accomplish it. So why is it that we decided to focus on Python for this class? I would start by saying it relies on an interpreter for execution. Now, relying on something doesn't sound like a strength, but in fact, it means that anywhere a Python interpreter has been written, your code can execute. So that is quite a lot of power. If we create software for Windows in Python, you can expect that with minor modifications, it will run quite happily on a Linux interpreter of Python or on a Mac. So being able to develop tools that can run on lots of platforms is available to you in Python. Python is also quite nice for emphasizing readability. You can write very brief code, very concise code that will make it a lot easier for you to maintain that code in the future. I don't know how many times I've experienced this, but I write some code on one day when I have some spare time, and then I come back to it months later and try to figure out how to add the next feature. And I spend a lot of my time just figuring out what was I thinking the last time, because the code is really hard to understand. But with Python, the readability becomes better, and our ability to understand the important parts of how the code is executing come together better. A lot of languages these days rely on curly braces to set off different sections of text. And especially when you have loops and decisions and so on inside each other, you end up with a great big nest of these curly braces, and it gets very difficult to tell which code corresponds with which block of code. So by getting rid of those braces, Python, again, improves the readability of code. If you do need your code to run very, very quickly, you probably don't want to rely on interpretation, on an interpreter like this. And if you want, it is possible to compile code written in Python so that it runs natively on this Windows machine or on this Macintosh machine. So that's very powerful, and having that ability matters if you're writing something that's numerically complex. And of course, lots and lots of libraries have been written already for Python that enable you to deal with files created in all kinds of different formats. So we will look at some of these libraries on the very last day of this 6-week session. All right, so let's talk about the project for this class. It's always better in my mind to have some sort of destination that you're heading toward. What program are you trying to create as a way to organize your thoughts about how to do it? Now, I've created a simple flowchart here. I've used just 3 of the different shapes available to us in flowcharts. So you see that we have the purple rounded boxes, we have the blue diamonds, and we have the blue parallelograms. So a blue parallelogram here represents some process we're going to undertake as we try to follow this workflow. Every blue diamond represents a decision, and all of those purple objects represent starting points or terminating spots for this code. So I think I mentioned this in the first email, but I'll try to reiterate. The intention of this class is to create a tool that can read a FASTA sequence database. This is a very common file format for storing sequence data in biology. We're going to count how many times each letter appears in the sequences of the proteins, in this case, that appear in that database, and provide some information to users about how commonly, how does that stack up, which letters are most common in the sequences. Now, how we get there is a little bit complex. Frequently, we don't think about all of the little steps. If you as a graduate student think, okay, I got to write a PhD dissertation, and you just think, okay, dissertation every day, you don't finish all the little steps that get you there. So it's a whole lot easier if you think, okay, well, I need to get this paper, and that other paper out. So what do I need to do for paper 1? Okay, I need to wrangle this data set. I need to do this type of analysis. I have these bench experiments. I have this statistical analysis at the end. Now you've got a series of steps that you can use to get to that first paper, to get to the second paper, to get to the third paper, and then to get to your dissertation. In the same way, programmers all the time have to be able to break down a complex program like the FASTA Sniffer that I've described. And they just think, well, I don't know how to get started. So it's a lot simpler, I think, if we try to break this down to tiny steps. In the end, we do not want code that solves just our problem of reading our particular FASTA database. We would like people to be able to use it with all kinds of FASTA databases. So one of the very first things that we're going to check in our program launch is, did the user provide the name of a FASTA file? If they didn't, it's kind of hard to move ahead, isn't it? So this is one of the first things we're going to have to do, and one of the things that a lot of people, I'm going to say this is true of graduate students in particular, but it's not limited to grad students in any way, shape, or form. Lots of grad students think, I need to make this code work for my project, and then it will never see the light of day again. And that's very short-sighted, because often you will discover that in your studies, you create tools that other researchers need to make use of. So it's always good to learn a few good programming habits along the way. So in this case, if somebody has not provided a FASTA sequence database name when they ran the code, we need to output to the screen how someone should use this program. You don't just launch the program, you launch the program with the name of the sequence database, and then terminate. This is a standard bit of coding that everybody should include when making a tool. If someone obviously doesn't know all the things they should have provided to the software, tell them what things they need to provide and die. That's a typical usage line. Okay, so if they have provided that, we need to try to open this FASTA file that they've provided. Now, it's possible that somebody mistyped the name of the sequence database that they expected you to read. So if that's the case, you need to tell them that. You need to report the error, not just die in some sort of ugly error message, but give them enough information to say, hey, this file you told me to look for is not here, and then die. Okay, so we've already seen two kind of stupid ways for the software to die, right? The person didn't know what they were doing. They just ran your code to see what happened. So you gave them some information and the software died. We checked to see if the FASTA they provided was real. If it is, we can go ahead. If they didn't, we need to go ahead and die. All right. So next, we're going to have something that we call iteration. Now, iteration is something that we're going to talk about a lot in a week from today. But for now, I'm just going to say that we don't read the whole file all at once and then try to build this frequency table of amino acids from the get-go. We're going to go through this bit by bit. So we're going to start by reading the FASTA file line by line, and then later on we're going to move to a sequence-by-sequence approach as we use a library for it. So can we read the next line? If we can, then we need to update the statistics. After we update the statistics, we then come back here and read the next line. If we can read it, we need to update the statistics. If we can't, then we need to come over here and report that there are no more lines left for us to process. We report our results, and the software dies. So does everyone understand the flow diagram? A lot of people just skip this step saying, well, I know what I'm doing. and then they end up writing a 1.0 version of the code that's really a mess. So it's often very useful to have what I call the blank whiteboard moment. You walk up to your chalkboard or your whiteboard, you clear off a space for just your diagram, and you spend some time thinking about the likely flow of that software. Okay, a lot of people, when they install the Python software, do not get the software on the path. A path is a way that the computer knows to look for the tools that you want to run. So I've given some very brief directions here for how to get to modifying that in Microsoft Windows. So I note that I've already outed myself as an old person when I said in Windows Explorer, right-click My Computer. My computer is actually an artifact of the old Windows 95 interface. So I'm going to pop out of slides here, and we're going to try to walk through these directions, but this slide should help you remember about this step. All right, so I have a Windows Explorer window open here. You see that I've created a directory right off of my root drive, off of C, called UWC Python. I'm going to talk about this directory a lot over the course of the next 6 weeks. So just as a way to organize your thoughts, I might suggest that you go ahead to move the 3 files you downloaded for today into that directory, into UWC Python. That will make things a little easier. Okay, so we see that my computer does not in fact show up anywhere on here. What we see instead is this PC, because I'm running a Windows 10 computer. So I'm going to right-click this PC and come down to Properties. Does everyone see that? All right. So when I click that, up pops what's called the System Control Panel. I wanted to note that anytime somebody asks you what kind of computer that is, what kind of computer you're using, you can find out right here. You can see that the processor is specified, how much RAM you've got. Are you running a 64-bit or a 32-bit version of the operating system? So this is actually a very useful place to be. But we're interested in setting environment variables, and to do that, we must go to Advanced System Settings up here. So I'm going to click on that, and now I have my system properties up. You can see that there's a little button down here for environment variables. I'm going to click that. So we see that path is one of the options we have. And if I click on Edit for path, I see all the different directories that are here. Now I'm cheating. Did you see that? Mine's already listed there. But if you don't have Python listed there, you probably need to know, how do I find where Python is on my computer? I mean, you don't have a user D tab on your computer, so you're not going to have that there. So how can we find Python? So I'm having installed Python already, I can hit the Windows key on my keyboard and then just start typing Python. Does that work for folks? All right. If I right-click that, I can open the file location. Is this working for everybody? Okay. And I see that I have, it is located Python 3.7 64-bit. Now that might seem great, but I want to point out that this is not, in fact, the software we want to run. This is a shortcut. So they've hidden it from us behind yet another layer. So I'm going to right-click that and say that I want to open the file location. So the first thing I was able to find was a shortcut to Python. In the second case, I found Python exe, and that's what I actually wanted to find. So Python exe is right here. We can verify that by double-clicking it and so on. The software will run. But what I really want is all this stuff up here. So you saw that when I just clicked on that top path, it turned into a bunch of text. We want to copy that. Right-click, copy. And I swear everyone will want to do this. I know it seems really kludgy to add path manually like this, but it's going to save you a lot of finding time in subsequent weeks. So we want to copy that text, come over here, and add a new item that is that path. Now see, I don't have to add it a second time. Just the first time's well enough. All right. So in the end, when I go to a command prompt, I want to be able to type Python and have the software know where to find it. So I'm going to redo the command prompt step. I'm going to click on the Windows button on my keyboard and type CMD. This is to open the command prompt. And now I type Python, and that happens. Does that happen for you on your computer? Does that happen for everybody? I don't think it happens for everybody. It does not happen. Okay. So on your computer, are you able to find the Python exe software? All right, let's walk through that. What's that? Okay, is Python installed on your computer? It was not? Okay. I'm sorry? Yes, I'll walk through that from the start. Okay. So since everyone's going to have this done, I'm going to walk through the process of how to find Python again. All right. Everyone was okay for getting to the place where we set environment variables, I think? Okay, good. But how do we find Python? I hit the Windows button and I type Python. And up pops the app. So I can open its file location right here, or I can right-click it, either way. But I see that what it's showing me is actually a shortcut, not the software itself. So if I right-click that and say Open File Location, this pops over to the Python directory itself. And here's Python exe. So there are different ways you can run Python. I mean, if I have a command prompt open, I don't have one at the moment, let me change that. If I open a command prompt, I could just drag Python exe over to the command prompt itself, and that'll work. But again, I have to be able to find it to do stuff like that. Oh, sorry. So instead, I want to add this to path. So I'm going to grab that text up there, copy that to the clipboard, come over to my system control panel, which I thought was open but isn't, and add it. So properties on that, advanced system settings here, environment variables there, here's path. I specify that I want to edit path, and then I can add that item to this roster using the new button. Okay, that part will appear on the video, so we may want to go ahead and press ahead. We have only a few more minutes before the other class comes. So, but adding the software to path will make it much, much easier to use all the examples that we're going to do. All right, I'm going to come back to the slides and talk about just a few more things before we move to some examples. I want to talk about a difference between functions and methods. Functions and methods. We use a lot of functions all the time when we're programming. One of the ones that shows up most prominently in the code example for today is the print function. And the print function does what it says. You feed it a bunch of stuff in between its parentheses, and it outputs that to screen for you. So that's a very helpful kind of function, but it's far from the only kind. So I thought I would give you an example of defining your own function. Here you can see that I'm defining a function called Euclidean. This is for computing what's called Euclidean distances. So if you have an x versus y plot, you have the value at 3, 4 is 3 units over and 4 units up, for example. So if you have that and other points on a 2D plot, and you want to determine how far apart they are, you need to compute what's called the Euclidean distance. So we can give this function an x value and a y value for the first point, an x value and a y value for the second point. Then the function will internally ask how far apart are those two x values, how far apart are those two y values, and then it computes the square root of the sum of squares for those two differences. I think most people might remember this from geometry class back in high school when we talked about right triangles. If you know that the A side is 3 and the B side is 4, the hypotenuse of that right triangle is 5. So 9 for the square of 3 plus 16, which is the square of 4, is 25. Take the square root, that's 5. Right? So this is a function that will compute that anytime you give it the numbers. So once you've run this bit of code, Euclidean gains a definition as a function, and you can give it these 4 values, and it will say, the Euclidean distance is 5, because 5 minus 2 here is 3. 6 minus 2 here is 4. The software will infer that the other side must be 5 in length. Okay, so that's an example of a function. However, methods are a little different than that. Now, I've mentioned object orientation before, and this is not the place for me to get into how object-oriented programming differs from functional programming or anything of the sort. But I would say that sometimes the data that you're after belong to a particular object. So let's take the example of test string 1. We are here defining an object called test string 1 that is equal to this string of characters. So I'm going to call that a string a lot, just so you know. So strings represent a series of characters like this. And here we've got some nonsense text that we've just stuck in there between quotes. So in Python, strings are objects. This array of characters functions as an object. So if I want to use the find method, I need to specify which object it's going to act upon. So the find method here is part of test string 1 because it's an example of a string. So if I run the find method, I'm asking it where in your string is this key found. In this case, I'm providing it the word ipsum, and I'm asking where within lorem ipsum dolor sit emet is ipsum found. Now I can also run that on test string 2, but there's a problem when I try to run that find on test string 2. Does everyone see what it would be? Yeah, not there. So if you're asked where within this string is this substring located and this string's not there, you have to give some sort of error code. So in this case, this method will return a -1 value to report it's not there. Okay, so we've seen functions and we've seen methods. In this case, the method is a lot like a function, except it belongs to a particular object. Okay, I want to talk about one other concept before we look at the source code for today, and that is what's called conditional execution. It more frequently goes under the name if and else. So the function here is pretty straightforward. I was trying to host a July 4th party last weekend, right? Why would I do a July 4th party? Because I'm an American. This is what we do. I'm going to have a cookout, hot dogs and hamburgers and some fries. It's an American party. We can call them fries, right? It's okay? All right, so I need to throw this party. But see, it's a weather thing. Because you can't really call it grilling out if you're huddling inside due to rain. And does everyone remember what the weather was like last weekend? Miserable, just pelting down rain. So one of the things that we did was to decide that in the few days before that party was to take place, we would look at the 5-day forecast and see whether or not it was going to rain on Saturday. So if it were going to rain, we would put off that party until this coming weekend instead, when we would call it a Bastille Day party. Does everyone know what Bastille Day is? Bastille Day is about the revolution in France. The Bastille was stormed on July 14th. So if you can't have a July 4th party, you can have a Bastille Day party, hopefully. And of course, we have some sort of condition we need to meet for that. If it's going to rain on the Saturday following July 4th, then have a Bastille Day party instead. code gives us the same kind of flexibility. So in this case, we're creating a variable called number. Number has a value set to 3. And very conversationally, you can just read this. If the number is greater than 0, then we should print positive. But it is possible that number is not greater than 0. In that case, we should print negative or 0. Did you notice that we didn't just automatically assume it's negative just because it's not greater than 0? Right? Because it could be equal to 0. Okay, so there are a few things going on here. We've already talked about a string masquerading as an object in the last slide. Here we've talked about a variable being set to an integer, but I've sneakily thrown in something that we call a Boolean as well. You see that we had this comparison condition. We asked, is number greater than 0? So what's the output of an evaluation like that? If number greater than 0. The condition there is number greater than 0. So let's now pull back into, oh, I don't have a command prompt open again. How bad is that? All right, I'm going to just come into command prompt here. Can you read what's on screen? Okay, if it's a little fuzzy in the back, I can increase the font size. I'm just going to start the interpreter by typing Python. This is not the normal way we're going to use it. Normally we're going to call a particular piece of code. But in this case, I'm just going to start the interpreter. So I'm going to say that A equals 3, B equals 4, and C equals 5. I'm still thinking about right triangles, aren't I? These things happen. Okay, so if I wanted to determine whether A equals 5, I would not use the equals symbol here. Right? It might be very reasonable in your mind to say, oh, if A equals 5, it doesn't like that at all. Because when you ask if A equals 5, you're not trying to set the value of A. Instead, you're asking it to compare the value of A to another value. So A equals 3 gives us A equal, when I ask it what is the value of A, it replies easily, A is 3. But I can ask, is A equal to 3, using 2 equal symbols in a row. Do you see what's happened there? Okay, so the software is evaluating an expression, and it's returning a true or a false value. That is a Boolean. And Booleans show up all over the place, even if you never create Boolean variables. It is possible, by the way, to say D equals true, E equals false. I can then say D, I hope I remember the syntax correctly. I didn't, shoot. There we go. So that might look very weird to you, but this is actually completely legit Python. Okay, so we can ask, is D equal to E? That's not true. We can ask, is D or E? That's true. We can ask D and E. That's false. We can even do little crazy things like D minus E, bang equals E. You see that? Okay, so let's walk through what each of these little comparisons are. This is the logical OR function, which means if either of these values is true, the whole thing is true. This is the logical AND function, meaning if both of these are true, this is true. It's not, because D and E have different values. I can ask, is D equal to E? Those are false. I can say, is D not equal to E? When you see a bang in a logic like that, it means not. Okay, so lots of little bits of logic there. In the case of our numeric variables, remember we had A, B, and C. We can ask A greater than B? Not true. B greater than A? That's true. Everyone following this? Okay, great. I don't want to just assume everybody follows that stuff because I've been thinking this way for a long time, and I want to make sure we stop on these. So in this case, when I say if number is greater than 0, we just set its value to 3. we see that that gives a result positive. Otherwise, it's going to say negative or 0. But there's more than just else available to us. So we have if number is greater than 0, print positive. Else if, you see that Elif? You can read that as else if. So if this first condition was not met, then we can ask, is the number less than 0? If so, print negative. And then if the number is neither positive nor negative, we can say that its value is 0. That's what this final else does. Okay, so that's conditional execution. I know that this can be a lot to absorb all at once, so I'm going to try to walk through the example text that we've created for the goal today. All right. So I have created just a brief patch of code. This is everything on screen is all I've written so far for this. This is the very first step of our FASTA Sniffer. So I'm going to try to walk through what each of these little bits of code do. We start with printing FASTA Sniffer version 0.1. Why is that important? Because when your software is called, it should identify itself in some way. And having a name, even if it's a silly one like FASTA Sniffer, is very good. If you are going to maintain this software over a long period of time, it's a good idea to keep version numbers associated with it, especially if you're working with a source code repository, which we will not be discussing in the course of this class. I think it's wise to include your name so people know who to complain to. If you're trying to dodge the slings and arrows of people complaining about your code, feel free to make it anonymous. But generally speaking, your university will claim copyright on anything that you create as a graduate student. Maybe later on when you start your first startup company. Have you guys started a company yet? I still haven't started a company yet, but I hear it's the thing to do. Okay, well, when you do that, then your company can copyright your code for you. And you should specify under what terms is it available. Here I've used a very standard way to say this code is free, modify it as you will. That's the GNU Lesser General Public License version 3. And then I just use print with no argument. You see that? I'm passing the function nothing. In this case, print will just add a blank line here. Okay, so for the very first version of this code, I decided that we would stick with something simple where we hardcode the name of the FASTA file. This is not preferred practice, but for day one, we're going to start here. We're going to start by saying this FASTA equals blah, blah, blah. Now that's an awfully long string, and in this case, it is the file name that we inherited from this Mycobacterium sequence that we're working with. How many of you have ever looked at a FASTA file? Not so many. A few? Okay, if you have, good. Well, I just want to explain that we are working with a protein sequence database. And this database is big because it contains every protein sequence known to be produced by Mycobacterium tuberculosis. Now, is it huge? Does tuberculosis have more or fewer proteins than does a human? Far fewer, far fewer. There are, I believe, less than 4,000 proteins in Mycobacterium tuberculosis. Something like E. coli gets by on like 4,200, I think. Something like yeast gets by on 6,200 proteins. But humans are like, well, we have 20,000 protein coding genes, and they produce somewhere like between 70 and 100,000 distinct protein sequences when we consider all the isoforms from them. Okay, so this database represents the list of all protein sequences. Now I want to note that the lines start one of two ways. They either start with a greater than symbol, which indicates that this is another sequence within this organism. This is its accession name, and then the rest of this is all just description. And because I've got my screen font set so large, it's not showing this one line on one line of text. But that whole first line starts at the greater than symbol and runs to where that cursor is blinking. But the rest of these lines are quite different because they're not English text at all, and they're not accession numbers. These are lines of sequence. So these are lists of amino acids that comprise this particular protein sequence. And it just goes on and on and on and on. It's a very long text file. So digging through this by hand is really painful and awful. But software can deal with this really easily because despite the fact that we call this a FASTA database, it's just a big text file. And every programming language out there can deal with text really, really handily. Okay, so when we look at our source code, this is the Python code that we're trying to create here, we see that we have created a string variable, this FASTA, equal to that file name. I've also created an integer variable called the FASTA count. So eventually this number is going to hold how many different sequences are there within this sequence database. Okay, so I note right away that we've hit a stopping point within the code. The software must stop right here if no FASTA has been provided. Now that little line of code there doesn't actually tell Python to do anything, because it's not a hashtag, I'm sorry. That tic-tac-toe, or that number symbol, as we used to call it, is a comment designed for your readers. People who are reading your source code should be able to figure out, what were you thinking? And I state that the number one most important reader of your source code is you 3 months from now, right? So make yourself little comments in here. Leave yourself a little white space like this. Add yourself some comments to tell you what were you thinking when you coded this bit. All right, so the software must stop right here if no FASTA has been provided. So you can see that I've used a function here. This is the len function. And len tells us the length of a string. So what I've asked is, what is the length of the string this FASTA? If it is less than 1, then we're going to tell the software to spit out a usage message and die. Do you remember that was on our diagram? And when we backed up here, we had this, if no FASTA file name is provided, output the usage information and die. We're actually coding all of that on day 1. So when we come back to our code, we see if this FASTA file name has a length less than 1, then complain about it. Your software is allowed to complain. So you can just say, no FASTA provided, exiting. Usage. This software will give statistics for the FASTA file provided on the command line. It should be run by saying Python blah 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 file name FASTA. I gave the wrong file name. This is from the last time I taught this class. Here, I'll just fix that. 711. There we go. Great. So this is how someone should run this code. And then after that, it runs this special function quit, which tells it to simply die and go right back to the user interface. Okay. Now, that's not the only condition we need to meet before we agree somebody has given us a legitimate FASTA file name. So we also want to look to see, does this contain this short string .fa? I see 3 different file names, file suffixes used when people give me protein sequence databases. The first of them is .fa. The second of them is .faa, because some people use FAA to represent an amino acid sequence database and FNA to represent a nucleic acids sequence database. And the other possibility is that somebody is going to give me a file that ends in .fasta, FASTA itself. But I want to point out that all 3 of these contain these 3 letters, .fa. So by looking for that, I'm covering all 3 of those cases, and hopefully they didn't put it in capital letters, because I think that would still cause this to die. So it's not airtight, but it's a starting point. Okay, so I will then report this file name does contain a FASTA extension, or the file name does not contain a FASTA extension, and it reports that name to the user and dies. That's the end of the code. So for day 1, we have not covered all the functionality in this code. We've just done a brief little snippet of its functionality, but enough to tell people how this code should be used, etc. So I want to point out that when I'm in the interpreter like this, I can't really run the code directly. So I need to get to the directory where I put the code, which was in It's in a directory off of root called UWC Python. I can do a directory to look at the files that are there. Because Python is on my path, I can just call it like that. Just type Python and get on with my life. All right. So you might notice I didn't type all of that out. I want to point out yet another useful thing to you. Okay, so I want to get this 2019-07-11 software to run. So I know that it starts with 2019-7-11, but I don't want to type the whole thing because the number one trait of programmers everywhere is we're lazy. The best motivator for every programmer is I don't want to have to do that by hand. We are lazy people. So in this case, I'm lazy. I don't want to have to type out -goal1.py, but I know that the file starts with 2019-07-11. I'm just going to hit tab. No relation. Okay, so when I hit tab, it automatically completes the rest of that line, and I can execute the software. So Python blah blah blah, in this case, tells it to look for a script named 2019-07-11 goal1py, pass it to Python, and run it as a complete program. So you can see that FASTA Sniffer version 0.1 showed up, my name, Stellenbosch University, GNU Public License showed up. You remember we had that if condition to check whether it does contain a FASTA file extension? The test passed. It says it does contain a FASTA extension. Now this is actually kind of bad form. I should tell the user I'm expecting lowercase .fa, but I'm not going to go into that detail right now. And it said, and in the end, the software reports, this is the FASTA we will use, Mycobacterium tuberculosis H37RV. Okay, so that's not bad for a first day. Please, please, please make sure that you have Python added to your path for the stuff we want to do on next week. If Python is not on your path, you can always check in with me before 9 o'clock or today after 11 o'clock, because I'm teaching the next hour, and I'll try to help you get that set up. Do other folks in the room feel ready to help others to get Python on path? Okay, a few people nodded. This is good. All right, so also consult among yourselves, and next week we'll be back to talk some more programming, this time looking into the great fun of iteration and understanding command line arguments. It's going to be great. Okay, see you then.